Previously, we learned about exponential and logarithmic functions. We then learned how to graph exponential and logarithmic functions, and then finally, properties of logarithms. Taking all that information together, we are going to learn how to solve exponential and logarithmic equations. Let's review the basic function of solving an equation. Whenever you solve an equation, that means you are finding all input values that would make the equation true. For example, if I'm trying to solve the equation 2x plus 1 equals 9, that means I need to find every value of x that would result in a true equation. And for an equation of this type, we've probably done this before. We would use algebra because we are going to isolate the x. Right now, the left side is saying 2 times x, then plus 1 should equal 9. So we can reverse that. If we're adding 1, then we can reverse that by subtracting 1. And that would yield the new equivalent equation, 2x is equal to 8. And what we want to keep in mind is this equation is equivalent to this equation. So the solutions, the x values that make the first equation true, are the same x values that make the second equation true because we got to the second equation through allowable manipulations. Now 2x equals 8, that means 2 times the number equals 8. We might think of that in our head, that means x has to be 4. And the way we would come to that is we would say it's being multiplied by both sides by 2. Let's divide both sides by 2. And we get our answer, x equals 4. Now for equations that involve exponential and logarithmic functions, we need to use properties of logarithms and exponents to solve these equations. To solve general algebraic equations, the only operations you need for these types are addition, subtraction, multiplication, and division. But logarithmic and exponential functions are different. In order to solve those, we'll need to rely on the knowledge that we've gained in our previous sections. So within these notes, we're going to look at several basic methods to solve exponential and logarithmic functions. And as we go through these, really try to pay attention to the strategies mentioned and the different structure that you see in the equation so that you can apply it to future problems. If you would like, there are more examples given in the textbook in this section of the notes, and you could read pages 390 through 398 for additional examples. Looking at our first example, think to yourself, is this an exponential equation, one that involves exponential functions, or a logarithmic equation, one that involves logarithms? This would be an exponential equation. Particularly, it's an exponential equation using the function f of x is 2 to the x. It's just in this case, instead of just the basic input x, we have the input x plus 1, and then in the other one, 2x minus 4. So we're saying what x value, when you raise 2 to that x value and add 1 to it as the exponent, would be equal to 2 to the same x value where you multiply it by 2 and then subtract 4. Now if we recall, 2 to the x is an exponential function. And one thing that we know about exponential functions is that they are one-to-one functions. For the function 2 to the x, the left side has an input of x plus 1 is the input to the left, and the input to the right is 2x minus 4. Now, each of these were inputted into the input of the function 2 to the x. So the way we need to see this is this entire expression, 2 to the x plus 1, is the output of 2 to the x when the input is x plus 1. Similarly, this entire expression is the output of the same function when the input is 2x minus 4. But what do we know about one-to-one functions? We know if we pick any output value, for a one-to-one function, if that output value is equal to another output value, then what that tells us is the input values have to actually be the same. So notice there is only one place in the graph where it could be at height 2x plus 1, but this equation is telling us the height 2x plus 1, or 2 to the x plus 1, is the same as the height 2 to the 2x minus 4. This can only happen, these are our inputs, this can only happen if the inputs are actually the same place. So notice how we're going about solving this equation is we are basing our information on exponential functions and then going back farther to when we learned about one-to-one functions back in chapter 1. Because exponential functions are one-to-one, if you're told the output value of one exponential function at a certain input equals the output of the same exponential function at a different input, then because of the one-to-one function property, we know that the inputs have to be equal. So solving this original equation simplifies into solving when are the inputs actually equal to each other. So in this case, I would call this the structure of 2 to some input equals 2 to the some input, means the inputs are equal. And while solving the exponential is difficult, whenever we rewrite it through the one-to-one property, now this is just solving a regular equation. And we can do so using our basic properties of algebra. Let's get everything with x to one side, all the numerical values to the other side. Why don't you take a moment and pause the video, solve it for yourself, and then unpause to check your work. Moving the x to each side, we'll subtract the x over, and that would give us a single x minus 4 equals 1. To isolate x, we'll add a 4 to both sides. And that tells us that x would have to be equal to 5. So the original equation is when x equals 5 here. Oh, sorry. When x equals 5. So this is actually at 6 because 5 plus 1 is 6. 2 times 5 minus 4, also 6. Now, one thing we want to keep in mind so that we can apply this to future situations is this only worked because it was an exponential function with the same base. It was 2 to something equals 2 to something. As we see in our next example, we have 8 to something equals 16 to something. Since these are not the same base, we can't use the one-to-one property and just let the inputs be equal to each other. However, we could think about it and say, well, 8 and 16 are related numbers. For instance, 8 is 2 cubed. 16 is 2 to the 4th. Now, why did I try to think of these as exponents instead of saying like maybe 8 is 2 or 16 is 2 times 8? Because we notice our x value is in the exponent, so we know we're going to be dealing with exponential functions. And exponential functions are best when we can get down to the same base. So instead of seeing 16 as 2 times 8, although that's true, it's not helpful, it would be better to ask ourselves, is there a certain fixed base that I could rewrite 8 as some exponent to that base and 16 as some exponent to that base as well? Using this would rewrite this to be 8 is 2 cubed, so we have 2 cubed raised to the x plus 2 as its exponent, equals, now 16 is 2 to the 4th, so 2 to the 4th being raised to the x plus 1 as the exponent. And here we'll need to remember some properties of exponents. If you have a to the b raised to the c, so a is the base, it's being raised to the exponent b, and then all of that is being raised to the exponent c, then this can simplify to a to a single exponent where we multiply the exponents, so a to the b times c. Using that idea, this would simplify to 2 to the 3 times x plus 2. Parenthesis use here is important because that shows the 3 is going both to the x and the 2, which is equal to 2 to the 4 times x plus 1 by properties of exponents. And at this point, think about what solution strategy we would use here. We see this as asking us 2 to some input equals 2 to some different input. This is the function 2 to the x. And we're looking at two different input values into this function. Since this function is 1 to 1, we know if the output values are equal. That can only happen if the input values are also equal. So by our 1 to 1 property, discussed here above, we know that this means that if the two equations are equal, then the two inputs are equal. And notice that this idea takes us from an equation that was quite difficult to solve into an equation that we've been solving probably for years. At this point, we can use algebra to solve it. To solve for x, I need to get x's all to one side, numbers to the other, but first we'd have to distribute. Why don't you take a moment and pause, solve for x on your own, and then unpause to check your work. So we have 3x plus 6 equals 4x plus 4. Okay. Subtract 3x to both sides. Subtract 4 from both sides. And we would get that x is equal to 2. And the good news here, in all of these problems, you can always check your work. If I was to check my work, I would go back to the original expression, plug in the x value that I found, so 8 to the 2 plus 2 is supposedly equal to 16 to the 2 plus 1. Let's check that. 8 to the 2 plus 2 is the same as 8 to the 4th. 16 cubed, and then we can get our calculators and just verify these are the same value. So 8 to the 4th, 8 times itself 4 times, 4,096. Let's see if that's equal to 16 cubed. 16 times 16 times 16, 4,096. These are indeed the same value. So that tells us that our x value that gave us this expression is the true answer. So we've just verified that x equals 2 is indeed a solution for our original equation. So let's talk over the strategy of this problem. It's somewhat of a hybrid of the last problem. We still use the strategy that if you've got an exponential function, 2 to some input equals 2 to some input, then since it's 1 to 1, you can equate the inputs only. So we just equated the exponents and then solve for x. In this example, there was an additional step because our original expression did not have the same base. So we first had to think off to the side, is there any way I could rewrite 8 as a common, like, some base to some power, 16 as that same base to a different power? And after thinking through it, we found that 8 is 2 cubed, 16 is 2 to the 4th. And the important thing here is now that would let us write this as an equation where we've got an exponential function of the same base. So we simplified the exponents through this property, and we got this expression. Same base to some exponent equals same base to a different exponent, means the exponents have to be equal, which we set up here. And at this point, we were solving it with our normal algebraic techniques. In our previous two examples, we saw a very similar solution strategy with a small change. Now for this next one, the same solution strategy does not apply even though we have something to some exponent equals something to a different exponent. And why don't you pause the video and take a moment to look at this equation and try to think about why would the same strategy not apply here when it applied to our two previous examples. So pause and think about it, come up with some ideas, and then unpause and we'll have a discussion. The reason the same strategy does not apply in this case is first, we look, it's not the same base. That was kind of like our first example. But in the second example, we didn't have the same base, but we still made it work. But that's because our base was 8 and 16, which could both be written as a power of 2. But if we look at the base of 5 and 4, there's no common base that we could say 4 is something to an exponent and 5 is that same base to a different exponent. These just don't work out. So since these could never be rewritten as some base to different exponents, we can never get into the idea where we have some base to something equals same base to something else. If we have this set up, then we can immediately let the inputs or the exponents be equal to each other. But we're not going to get that here because there's no way we can rewrite 4 and 5 easily to a common base as an exponential. So we have to have a different strategy. So even though it looks similar, we realize the previous two strategies don't apply here. So what we're going to use instead is one of these properties. Because we know our goal is to solve for x, but where is x? It's in the exponent. You can't multiply, add, subtract, or divide your way out of an exponent. There's no way our previous 4 main operations would allow us to do that. So when your variable is in the exponent, you've got to then turn to the ideas of exponential functions and logarithms. So we need to solve for our variables in the exponent, and the first thing is to try to get them out of the exponent. And the way we're going to do that is this property. Now we don't have a logarithm here, but we could create a new equation that does have a logarithm, and the reason that we'd want to is notice we've got some base to some exponent. But in this rule we had u to the n power, but what did it say it's equal to? If you have the logarithm of some base to some exponent, then it's equal to the exponent as a multiplier of log of u. And the reason this is great news for us is it brings the pesky exponent out in front in multiplication. So it gets rid of the problem. The problem is the exponent, or the variable is in the exponent, but if we apply this principle, we'll be able to bring the variable out of the exponent. And notice here, this was log base a, and this exponential function was u to the n. So the bases don't have to be the same for this property to work. So what we're going to do is we started with this equation, but if I consider log, and I'm just going to use log base 10 of 5 to the x plus 2, what I'm doing is I'm creating a new expression. I know I want to bring 5 to the x plus 2 inside a logarithm so that the exponent will become in front as multiplication. But I don't want to just stop here because I need an equation that I can manipulate and work with. So I think about what is 5 to the x plus 2 equal to? Well, at the very beginning they told us 5 to the x plus 2 is equal to 4 to the x. So I could equivalently write this is equal to log, but instead of 5 to the x plus 2, it's 4 to the x. So we now have an equation that we can work with. And by this property, we know that the exponent of the input of a logarithm comes in front as a multiplier. So we could write the new equation, x plus 2 all times log of 5 equals x times log of 4. And while definitely these two things look complicated, log of a number is just a number, and specifically it's a number that your calculator knows. We could easily type this into our calculator, but I'm going to wait until the very end just so I'm not writing out tons of decimals. So this is basically x plus 2 times some number equals x times some number. This is an equation that we can solve. Specifically, the way we would do so is we need to get all the x's to one side, but in order to do that we need to simplify things first. So I'm going to distribute this numerical value of log of 5 to both terms since it was getting multiplied on the right. There's nothing to, or on the left, there's nothing to do on the right. This would be x times log of 5 plus 2 times log of 5, and that's equal to x times log of 4. Now the strategy here whenever we're solving for x and it's now flat, it's no longer in the exponent, is to eventually get all the x's to one side, all the numbers to the other side. So since we've got a singular x here, Let's move this x over. It's currently being added, so we could subtract it over from both sides. Cancels from the left side. And then here, in this case, since it's x times log of 4, x times log of 5, these aren't the same thing, so they can't combine to a common term. We would just have to write them being subtracted by each other. Good news is now the variables are all on the same side. Bad news, there's two variables. What could we do here next? Whenever you have the same expression on either side of a plus or a minus, then you can factor out that common term. So we could factor out an x from here and an x from here. In the process of factoring out an x, it takes what was two x's to a single x, which is our goal. Let's factor out the right side. If you take an x out of this term, that just leaves you with the log of 4. If you take an x out of this term, that just leaves us with the log of 5. All of this was equal to 2 times log of 5. Now, it's a lot of symbols, but we're going to stay focused. This is some number your calculator knows. This is some number your calculator knows. This is some number your calculator knows. We just have to keep writing it and then eventually type it in correctly to our calculator. We've almost solved for x. The only thing is that we have to see that x is getting multiplied by this number, whatever it is. So if we had 2x equals something, the way we'd solve for x is we divide by 2. Now we have x equals this numerical value, so we just divide by it. It just happens to look a little more complicated, so we're going to divide both sides by this expression. Keeping this in parentheses. What's done to one side must be done to the other. Cancels from that side, and that would leave us with x equals 2 times log of 5, all divided by log of 4 minus log of 5. And for these ones, in your future Canvas quizzes or exams, there will be some instructions round to so many decimal places. Let's say that this has round to 3 decimals in your final answer. So notice I kept carrying all the expressions until the very end. Now I'm going to type this into my calculator. And anytime you're typing a fraction into your calculator, I recommend you keep all of the top together in parentheses and all of the bottom together in parentheses as well. So let's type this in. If you have a calculator, be sure to be attempting this along with me. So I'm going to take my parentheses first. 2 times, now in my calculator I have to type the number and then type the log. Probably in yours you would press the log button first and then the number. Mine is just a little strange since it's on the computer. So 2 times log of 5, close the parentheses to show that I'm done with the top of the expression. Divided by, okay, I'm going to open the parentheses for the denominator. I'm going to type the log of 4. Again, probably in your calculator it would be log and then 4 minus, okay, close parentheses to show that I'm done. I check I've got the parentheses surrounding the top, the numerator, divided by the parentheses surrounding the denominator, log of 4 minus log of 5, press enter, and I would get negative 14.42513,487, and it did say round to 3 decimal places. So going over, that's 1, 2, 3. Looking past the 5, it's a 1, which means we wouldn't change the value. So it's just going to be negative 14.425. Take a moment to pause the video and try to describe this equation to yourself in words, what's occurring here. So take a moment just to assess the situation, unpause when you're finished. So first, I notice I'm working with an equation. An equation is nice because it means I can manipulate both sides. the left side is 4 times e. We know e is the number 2.718 that continues on forever, so e is never a variable, it's always representing that number, raised to the exponent 2x. So here I notice, oh, the x, what I'm solving for, is in the exponent. That means I'm going to have to use different strategies than the basic 4 operations of algebra. And then what do you do after you say 4 times e to the 2x? You add 5 to it, and after you've done that, the resulting value is 12. So we need to solve for what x value when you say e to the 2 times that x value, multiply it by 4, and then add 5 gives you 12. And if we compare this to our previous 3 examples, we see this as a somewhat different situation because there's only one variable, just x, and the right and left side, the left side has an exponential equation, and the right side is just a numerical value, as opposed to our previous examples where it was some exponential function equals some other exponential function. So what I would say is our goal is to solve for x, which is inside the exponent. But in addition to it being inside the exponent, there are the 4 basic operations of algebra going on here. We are adding 5 to the 4 times the 2x, we're multiplying that by 4, and then the result is 12. So why don't we simplify as much as we can with the 4 basic operations of algebra, and then with what's remaining try to figure out what the next step is. For instance, we could subtract 5 from both sides, because the 5 is being added, so if you subtract it from the left and you do the same thing to the right, it keeps the equation equal. And now we're looking at a much simpler equation. So it would be 7. Now, we still need to solve for x, and it's inside the exponent, but before then, we're multiplying 4 times that expression, so we could divide both sides by 4. It's being multiplied, so do the opposite. That cancels it from the left side, and we'd be left with the simpler expression e to the 2x equals 7 divided by 4. And while I could type that into my calculator, okay, in this case it's a nice decimal, but if it had been a super long decimal, in that case you'd probably do better to keep it in fraction form, but in this case 7 divided by 4 is a nice decimal. I can leave that as 1.75 if I prefer. But generally don't round in intermediate steps if it had not been such a nice decimal. Okay. So at this point we've done all that the 4 basic operations of algebra will allow us to do. And now we're stuck with trying to figure out how do you solve for x when x is in the exponent. We can't multiply, add, subtract, or divide our way out of this. And unlike our previous examples, the right side is not e to something, because if it was, we would just allow the exponents to be equal, but that's not the case here. 1.75 is not an exponential function. So take a moment to look at these properties of logarithms and ask yourself which of these properties gets rid of exponents. This doesn't apply to exponents. This seems to apply to exponents because we started with an input of a to the x, and then we just got the exponent back as a result, so we'll keep that for now. Doesn't apply to exponents. This has an exponent, but not in the way we want. We're not doing a to some logarithm. We've got a base to some exponent, so that probably doesn't apply here either. Doesn't help us with exponents, doesn't help us with exponents, doesn't help us with exponents, does help us with exponents. So you've got 2 things here that help you with exponents in your properties of logarithms. Take a moment to look at these 2 and ask yourself what would be the most efficient strategy. They're both going to work, but one would be more efficient than the other. Why don't you pause the video while you're investigating this? Unpause when you're done investigating. Okay, so looking here, I would say this applies in a nicer way, because notice what's happening is if you have log of some base a whose input is that same base a to an exponent, what it's saying is if you form the left side, that is equal to just the exponent x. Whereas this side would also work, but since the bases don't match, this is a, this is u, it doesn't simplify as nicely. So if you can ever apply a logarithm that matches the base of the exponential function, things simplify a lot nicer. So I'd ask myself, what logarithm has base e? Log base e of x is the same thing as natural log of x. So if I would apply a natural log to this side, natural log of e to the 2x, by this rule it tells me natural log if the bases are matching, which they are here, then since these are inverse functions, natural log and e to the x, what I get back is just the input as a result. So you can imagine these canceling, it's through inverse property, and then all we would get is 2x. So we've been able to get the exponent down, but this isn't helping us because it's not in the frame of our original equation. So we need to take this a step further. What was e to the 2x equal to? Well, e to the 2x was said to be equal to 1.75. So we could form the equation natural log of e to the 2x. This is the same thing as applying natural log to both sides. Natural log of a number is just a number. And what do we know the left side simplifies to? It simplifies to just 2x. So natural log of e to the 2x, we would get 2x on the left because the exponent is all that's left, equals natural log of 1.75. So to solve for x, all we would need to do is divide both sides by 2 and type this into our calculator. So we would get x is equal to natural log of 1.75 all divided by 2. This is something we'll want to type into our calculator, so we do natural log of 1.75. Do make sure you use the natural log. Then divide that by 2. And for these problems, when it comes to our quizzes or exams, you'll be given rounding instructions. Let's say again we're rounding to 3 decimal places. 2.79, looking after the 9 is 8, so that rounds this up. But to round 9 up, it actually is going to take this whole term to 80. So we're going to get 0.280 when rounded. And we just indicate it was rounded by our squiggly equals. And as before, if you want to check your answer, then you can always do so by substituting back into the original expression. So our original expression was 4 times e to the 2x, then adding 5 would get us to 12. So with our rounded version, we could say 4 times e to the, now be careful here, we have to have 2 times x, so it would be 2 times 0.280, close parentheses. And then we have to add 5 to that. And notice that's almost exactly 12. The reason it's not exactly 12 is we did round our value to get 0.280. If we had left it exact and then plugged into our expression, we would get exactly 12. But this is close enough that with our rounding, we realize we got the correct answer. So your solution strategy here is you recognize this is some exponential expression, and then algebraic operations, we are multiplying by 4, adding by 7, and it equaled some numerical value. So what we did first is we said, well, this expression could be simplified using our 4 operations of algebra. So I moved the 5 over to both sides, I divided by 4, and we had a much simpler equation to look at. Once we simplified all we could using algebra, we said, okay, the goal is to get the x out of the exponent, but right now it's in the exponent of e to something. So I looked at my properties of logarithms, and I realized that if I have log of the same base of e to some power, I'm just going to get that power back as a result. So I set up the equation natural log of the left side equals what's done to one side must be done to the other, natural log of the other side. Now natural log of e to the 2x just became 2x. Natural log of 1.75 is just some numerical value. So at this point we had 2 times x equals some number. To solve for x you would divide both sides by 2 and then type it in our calculator, and that's how we would go about solving this example. Take a moment to look through our next example and try to describe yourself. What do you see occurring in this equation? If we can give words to it, we'll have a much better chance at solving it. And why don't you pause the video to do so and unpause when you're done, and we'll discuss this problem. Now looking at this example, the way I would describe it is, first I'm looking for, if I'm solving an equation, I'm solving for a variable. So I identify where is my variable. It's inside the natural logarithm as an input. Now when your variable is inside any type of logarithm, you can't just multiply, add, subtract, or divide your way out of that. So I know I'm going to have to do something different. Specifically, I'm going to use these properties of logarithms at some point, but let's see what else is going on in the expression. I have 2 being multiplied by natural log of x that I then add 3 to, and the result of all of this is equal to 7. And we want to solve for what x value when you say natural log of that x value times 2 plus 3 would give you 7. Now we know our goal is to get the x by itself, but before we can do that, we're going to have to eventually deal with the logarithm. But before you deal with the logarithm, which is going to be more complicated than we're used to, we would like to get this expression as simple as possible. Is there anything that you can see that we could do here to simplify this expression using our basic 4 operations of algebra? We could move the 3 and the 2 over the other side, because the idea is eventually we want to get x by itself, but you do that by moving everything that does not involve an x to the other side first. And between the 2 and the 3, you always move what's quote-unquote furthest from the x. So right now, what happens is the x goes into the natural log, and then it gets multiplied by 2, and then you add 3 to it. So I would say adding 3 is furthest from the x, so we're going to subtract both sides by 3 first. Do the opposite, it's currently being added. That cancels it from this side, and we would get the equivalent expression 2 times natural log of x equals 4. Because if 2 times natural log of x plus 3 equals 7, then it's true that just 2 times natural log of x should equal 4. Now we see that if we want to get x by itself eventually, we might as well move the 2 first, so we're going to divide both sides by 2, and this is essential. You do need to simplify the side that's involving the logarithm as much as possible before you apply any of these more complicated terms. So that would give us natural log of x, these cancel, is just equal to 4 divided by 2 is 2. And now we're looking at a much more simplified expression. Now you could use a property of a logarithm to solve it at this point, but I would say that if you could rewrite this as an exponential equation, you're going to be able to solve it in a much more efficient way. So remember, every exponential function can be rewritten, every logarithm can be rewritten as an exponential function. This is an implied base e. Take a moment to pause the video and rewrite this expression as an exponential function. So we know to rewrite as an exponential, we keep the same base, so it's base e. Since they're inverse functions, the output of one becomes the input of the other, the input of one becomes the output of the other. So the output of the original becomes the input to the exponential. The input of the original becomes the output to the exponential. And this was back when we first introduced exponential and logarithmic functions earlier in chapter 4. And through this way, instead of having to solve for x, we now have x equal to some expression. Well, x is equal to e squared, or if we wanted to use our calculator, we would just take our e and then square that and get 7.389 when rounded to 3 decimal places. And that would be a great way of how we could solve this problem. Now, how do we know that this would be a good solution? I would say if you ever have logarithm of simply the variable is inside the logarithm and it's equal to some number, so if you ever have log of a known base of some variable equals some other number, I'm going to call this number 2 since this is the first number, they're not necessarily the same, then a good solution strategy at that point, the most efficient one, is to rewrite as an exponential expression, because that's going to switch places. Instead of the x being inside the input, it's now going to be the output, which means it's technically solved for. X is by itself. So you could rewrite this as x to, we always switch input and outputs. The output of the original becomes the input of the exponential, and sorry, we keep the same base, so this should be the number there. The number of the base raised to the number 2, the value that it was equal to, is going to be equal to x by definitions of exponential functions. But we did have to do a bit of algebra first before we got into this format. So just keep in mind, if you ever have a log of some known base of some variable expression equals some number, the best solution strategy is to rewrite it as an exponential function, and then you'll solve for it there. Okay, for our next example, I recommend you take a moment and pause the video and just try to describe it to yourself in words. Unpause when you're ready to think about it. So the first thing I notice is I've got a natural log on both sides, and that's a good thing because that means this is base e, this is base e. It's a logarithm where I've got 2 logarithms, but the base of each logarithm is the same. So that's good news. So logarithm of some input equals the same logarithm ln of a different input. So these are both output values. This is an output value when you've got the input x squared. This is an output value when the input is 2x plus 3. What is it the output value of? It's the output value of the function ln of x, which we know has the graph that looks like this. Now this is visually a one-to-one function, and indeed we know exponential functions and logarithms are one-to-one. Also, because we know that those are inverses of each other, we know those are definitely one-to-one functions because only one-to-one functions have inverses. So what this is saying is if you go over to x squared, wherever that is, and you go up to the output value, since this is our function ln of x, that's ln of x squared. What is it telling us is that this height is equal, that's what it said, equal to ln of 2x plus 3. So for some other input, 2x plus 3, if you look at that input, you're going to get to the same height. But the only place this function gets to this height is right here. So that tells us that the inputs must be the same by the one-to-one property of the logarithmic function. For one-to-one functions, if the output values are equal for a one-to-one function, then whatever the input values are, those must also be equal, because there's no other place in this equation that is at this height. Since there's no other place, then the locations that prompted these places must be the same. So that's kind of our reasoning here. So since it's natural log on both sides, it's the logarithm of the same base. So whenever you have logarithm of same base equals logarithm of same base, what you can do is you can immediately say, well, the inputs must be equal. And the reason this is beneficial is we've now been able to extract our variable expressions from outside of the logarithms, because right now, being inside the logarithms, we couldn't solve anything. So using the one-to-one property, because of this concept, we are now looking at just solving this equation. Now, since I've got a quadratic here, I think my first step is to get everything to one side and maybe hope that it factors, and if it doesn't, then I can use the quadratic formula. So I'm going to move everything over. I'm going to subtract a 2x since it's positive. Left with a positive 3, let's subtract 3. And that would give us x squared minus 2x minus 3 equals 0. Now let's see if this factors, and why don't you take a moment to think about whether the left side factors. Pause the video while you're thinking through that, and after you've thought through it, unpause to check your work. Now, there's many ways to factor. Feel free to use whatever strategy you prefer. I'm just going to talk through one method. I always look at the sign in front of just the constant term. It's negative. And this constant term came from multiplying this term and this term together. The only way you can multiply and get negative is if one of them was positive and one of them was negative. Okay. Now, x squared can come about, we hope, just by an x times x. There are other ways, but they're quite a bit more complicated, so we're going to hope it factors nice to x plus something times x minus something. And then we think, although it does not have to be only integer factors, if it's going to work out nicely, we would ask ourselves, what integers multiply to give us 3? And that would only be 1 and 3. So we've got to decide, where does the 1 go and where does the 3 go, because they're going to be different signs based on which location. To know that, you look at the sign of the second term. The second term is negative. That means wherever the 1 and the 3 go, we want the negative term to be the larger number so that we've got more negative terms, so that when we add the positive term, it still stays negative. So that would indicate for us that we're going to have a minus 3, but a plus 1. And you can always check your work. You can FOIL this out. And you would definitely get x squared minus 2x minus 3. Now this factoring is helpful because it's very difficult to see the solution here. But realize what the factored form tells us. It tells us something times something else equals 0. The only way you can multiply two things and get 0 back as a result is if one of the things is separately 0. So it allows us to take a complicated expression and turn it into a simplified one. We just have to know, when is the first term equal to 0 and when is the second term equal to 0. Because if either of these terms are equal to 0, then 0 times anything takes you to 0. And that's kind of called the zero product property. Now x plus 1 equals 0 only when x equals negative 1, subtract 1 from both sides. X minus 3 equals 0 only when x equals 3, add 3 to both sides. And that would be our solutions, and normally that's all we have to do. But a word of caution here, where did the original expression come from? It came from natural log of x squared, natural log of 2x plus 3. So whatever our x values are, they would have to be inputted back into this expression, and one thing we know about natural log is it only accepts positive values. So we would need to make sure if we inputted these x values into either x squared or 2x plus 3, do they stay positive? So for instance, negative 1 squared is positive 1, so that was fine. Because remember, it's not that natural log of x only has positive values, but natural log of x squared has a different domain, because you first take the x value and square it before you input it to natural log. So negative 1 squared is 1, natural log of 1 exists. Okay. Plug 3 into this. 3 squared is 9. That's fine. It's a positive value that we can plug into natural log. Let's check the right side. 2 times negative 1 is negative 2. Plus 3 is 1. Plug 1 into natural log, you'll get a real value. That's totally fine. And then into the same expression, 2 times 3 is 6. Plus 3 is 9. 9 is a positive value, so we can substitute it into natural log. So in this case, these are both our answers. But if your equation involves natural log, you do have to go back into the original expressions and verify that when you substitute the found values, it doesn't violate the domain constraints. So these are indeed our final answers here. Now, our last example of these notes is a word problem. Why don't you take a moment to pause the video and read through the word problem, and I recommend you read through it twice. Read through it the first time, just reading, and then the second time, try to extract some information, and then unpause after you've read through this example 2 times. So as we read through this, we saw that we've got two quantities, atmospheric pressure, which is in pounds per square inch, and then miles above sea level, which is denoted by x. Now we're asked to the nearest foot, and here we might be cautious because foot is a measurement of distance, but mile is also a measurement of distance, so we see that we have different units. So in my mind, I immediately know before I end the problem, I'm probably going to need to do a unit conversion, so I just write that off to the side so that I don't forget to do it, because there's going to be a lot of work, but we need to remember at the very end to change the units. How high is the peak of the mountain with the pressure being this? Now we can write an equation based on this statement. The pressure is this number. What represents pressure is P. So I would write off to the side P equals 8.369. And they've told us an equation that relates the height you are above sea level in miles to the pounds and pressure per square inch. So this formula will be followed. So what we've been told is a p-value, and we're asked to find the height, which is an x value. So we can substitute the 8.369 in for p, and that would give us, always substitute for what you know. And we know if we find x, we will have found the number of miles above sea level, but we want to find the nearest foot. So what we're going to do is we're going to find x is equal to something in miles, and then we're going to convert that to feet using this unit conversion they gave us here. So we're not going to worry about the unit conversion until the end. To start with, we need to solve for x. Take a moment just to assess this equation structure. How would you describe it to yourself? I would say I know I need to solve for x. Where is x? It's in the exponent of an exponential function. So at this point I know I'm going to have to use properties of exponential functions or logarithms to solve this in the end, because I can't get variables out of exponents without those properties. Again, you cannot multiply, add, subtract, or divide your way to get a variable out of an exponent or out of a logarithm. But before I solve for x, I see that although this would take a more complicated approach to solve, there are other things that I could simplify. For instance, I have 14.7 being multiplied by this term, and then the result is a number. So why not undo the multiplication first and divide both sides by 14.7? Because that's going to simplify both sides of the expression. Now I'm going to type this into the calculator and see if it's a nice round decimal, and it's not. And I wouldn't want to round this here yet, because if you round in intermediate steps, it's going to throw off your final answer. So what I would say is, even though it doesn't look as nice, let's leave this as a fraction, since it doesn't simplify to a nice simple decimal value. So I'm going to leave the left side as 8.369 divided by 14.7, because in the end we can type this into our calculator and then round the final answer, and that's going to be equal to e to the negative 0.21 times x. And now we take stock of where we're at. We've got our variable still in the exponent of e, but the good news is the right side is fully simplified. It's e to some power equals some number. So we think, how are we going to be able to get the variable out of the exponent? Take a moment to pause the video and look through our previous examples that we've done. You are going to find a similar solution strategy there, and then unpause after you've found it or attempted it on your own to see the solution. Now, our solution strategy is, in order to get a variable out of an exponential function, particularly when the base of that exponential is one of our nice bases, both e or 10, because we know that corresponds to regular log for 10, natural log ln for e, we're going to use this strategy, where if we have the log of the same base of that exponential function, that would simplify to just x, or in this case our exponent, negative 2.1x. So what we're going to do is we're going to take the natural log. The reason I'm choosing natural log is it's the same base as e, and I'm going to take the right side. But in order for this to work, we wanted to solve an equation. So if we've taken the natural log of one side, we do have to take the natural log of the other side as well. What's done to one side must be done to the other. Now we know that this side, through this property, natural log base e of e to something, just becomes the exponent, so that simplifies to negative 2.1 times x. And although this right side now looks complicated, we're not concerned, because we know that 8.369 divided by 14.7 is just some number. Natural log of some number is some other number that our calculator knows. So we need to do our last step to solve for x. Think about what that would be. The only thing standing in the way from x being by itself is that it's being multiplied by negative 0.21. So we would just divide both sides by negative 0.21. And in this case, be careful, the negative 0.21 is not going into the input of the natural log. You're finding this first, and then you're dividing by negative 0.21. So that gives us x is exactly equal to the natural log of 8.369, all divided by 14.7, which is all divided by negative 0.21. At this point, x is fully simplified on its side. Now we would need to get our calculator, and let's round this again to 3 decimal places, and just follow the rounding instructions for the quiz and the exams in Canvas. So x is equal to, equivalently, or approximately. So whenever you type a fraction into your calculator, if you're doing it all at once, be sure to keep the top of the fraction in parentheses, the bottom of the fraction in parentheses, because if it's not typed in correctly, the fraction will give you the wrong value. Now, in my calculator, I have to type the input first and then natural log, but yours is probably the opposite. So I've got the natural log of our input, close parentheses because I'm done with the top of the fraction, divided by the bottom of the fraction, close parentheses there, check to make sure everything's correct. And we would get this value. Now we're going to round that to 3 decimal places, so 2.682. Looking past the 2 is a 4. Unless it's 5 or greater, it stays the same, so our value is x is about 2.682. And here we need to be careful, x is in miles, so this is in miles. Looking back at the problem, they actually asked for the nearest foot. So we've almost finished the problem, but there's a little bit more that needs to be done. We need to take this mile measurement into a foot measurement, and they've told us for a single mile, 1 mile equals 5,280 feet. Now with unit conversions, you're always going to either be multiplying by the unit conversion value or dividing. And the key is just figuring out which one. We are going from miles into feet. Now 1 mile is this many feet. Do we see that we have 2.682 of those miles? And each of those should be about 5,280 feet. And the way you think about it is, if you're measuring the same distance, it's the same in either mile or foot. But if you were describing it, it would have to be many more feet. It's going to look like a larger number in feet to measure the same distance in miles. So since the feet value should be larger, that tells me I'm going to multiply. So I'll take the 2.682, the rounded value, multiply that by the conversion factor, and that would be my value in feet. So let's find that with our calculator. 2.682 times 5,280, and that would be about 14,160.96 feet. So in this case, we were given an equation that involved an exponential function. We were given a certain output value, and we had to solve for what input value, when plugged into that function, corresponds to that output value.